Hello from the world of renewable energy. Previously, we've talked about solar power and how it's a fascinating combination of innovation and sustainability. Today, the idea will be exploring the photovoltaic effect. It's a phenomenon using which solar energy is generated. But we need to first know the three types of solids, namely insulators, semiconductors, and conductors of electricity. They differ from each other with respect to their energy levels, or bands, or presence of electrons. The two most important bands are the valence band and the conduction band. The lower energy band, known as the valence band, is where electrons are firmly interlinked with their corresponding atoms. Electrons are in their lowest energy states and are engaged in chemical bonding, which actually holds the atoms together to form the solid. The material's chemical properties, as well as the way it would interact with other substances, depends on the number of electrons in the valence band. The energy level, or band above the valence band, is the conduction band. And this is where electrons can move freely about the material as they are at a higher energy and aren't bound to any atoms. Here, they're free. The difference in energy between the conduction band and the valence band determines the space between the bands. The two bands in conductors overlap partially or fully, thus making it easy for the flow of electrons from the valence band to the conduction band, which in turn leads to their high electrical conductivity. Conversely, insulators have a large energy difference between the bands, and so the band gap is larger as well, making it difficult for electrons to freely move between the two bands. This is the reason for their low electrical conductivity. However, there is a sort of magic that happens with semiconductors, the material used in solar panels. They have a small energy gap between the bands, and the electrons can easily jump from the valence band to the conduction band when additional energy is applied to the material or when it is exposed to high temperatures. This energy can be in the form of light or through doping. Intentional doping is done in different parts of the semiconductor material by introducing some sort of impurity into its crystalline structure or lattice in order to modify its electrical properties, which creates an electrical field in the material. The impurity has an additional charge, either negative or positive, depending on the impurity introduced. N-type or negative type doping is when an element with more valence electrons is added in trace amounts to the semiconductor, such as phosphorus or arsenic, which have 5 valence electrons, as compared to silicon's 4 valence electrons. The doped element replaces some silicon atoms, thus creating an axis of negatively charged electrons, as each introduced atom donates an extra electron. Similarly, p-type or positive type doping adds elements with fewer valence electrons, such as boron or gallium to silicon, thus creating an axis of holes in the silicon structure. Holes are the space where electrons used to be present and are positively charged. With the basics covered, we can move on to the photovoltaic effect. Solar panels are mostly made out of silicon, a semiconductor. When the photons or packets of light's energy in sunlight hit the silicon, the electrons get excited within the material. When these negatively charged electrons are free, they leave behind holes and create what is known as an electron-hole pair. These carriers of charge can be separated by an electric field and can be collected to generate an electric current, which can produce usable electricity. Light energy being converted directly into electrical energy is known as the photovoltaic effect. This effect is similar to the photoelectric effect, but with one key difference, that the electrons stay within the material in this effect, but escape the material in the photoelectric effect. Two layers, one N-type and the other P-type, that work together to control the flow of electrons, make a semiconductor more effective. Electrons travel from the N-type region to the P-type region to fill the holes when these regions are brought together. As a result, the boundary between both areas develops an electrical field. Acting as a barrier, the electrical field prevents electrons and holes from recombining, which would lower the solar cell's efficiency. And as said before, the electrical field helps efficiently collect the charge carrier at the solar cell's contact, generating useful electricity. This energy produced by solar panels is in the form of direct current and can be converted to alternating current, which is most widely used for household appliances and devices. The energy can even be stored in batteries for later use. This is how solar panels work, and if you like this video, be sure to interact with it and subscribe to our channel for more such content. And as the photons say to the solar panel, we are always energized to see you. Thanks for watching, and until next time. Bye.